Hi, my name is Emma Sandidge, and I'm here with
Priti Finavia.
Vincent Andrews.
We are team 1087 with our coach Anthony Stefan from Florida Tech, and we'll be presenting Problem B, Punishing Infants. In this presentation, we'll be defining a problem, make some assumptions, and our criteria for the solution. We'll create a model based on this assumption and perform a numerical solution to analyze the model performance. At the end, we will describe our limitations and further applications. So our problem describes the infant's ability to recognize aggressive behavior towards the third party and their desire to punish those individuals. Our goal here is to model a population that Our goal here is to develop a model that describes the development of the population that contains this individual with some affinity towards third-party aggression and observe how they evolve with time. Here, we will develop a model explaining how different populations change over time and observe the long-term population stability. We will explore steady-state solutions for different populations and use our software to run numerical simulations on real population statistics to judge our accuracy. For this model, we are assuming several things. One of the main important things is that individuals who are recovered from this aggressive behaviors do not become reinfected. And every person in the society is connected to at least one person.
So for developing our model, we took this image from the paper given to us in the problem, which shows an infant's reaction to physical stimuli. So they run several experiments with a stone falling on an individual. They change the material of the stone to see how this would influence the child's reaction. So we decided to extend this principle of reacting to third-party or performing third-party aggression from reacting from physical stimuli to observe how a society changes over time due to the presence of people with this aggressive propensity. For creating our systems of ODEs, we decided to model population dynamics with a SIR model, a susceptible infectious recovery, epidemiology model, and then we adjusted the parameters to fit the needs of our behavior analysis using lambda as the rate of infection, beta as the rate of recovery, and mu as the rate at which people are born or die in the population. All of these parameters we assume are greater than 0, and the susceptible population is essentially all the individuals who can be affected by this aggressive propensity. The infected population is people who have this aggressive behavior, and the recovered is people who have seeked out treatment and have become no longer aggressive.
So now we're going to do some stability analysis of the model solutions. And before we do this, we're going to verify that the system is bounded so we can perform this analysis. We can write the total population at time t by the sum of the three different populations, so the sum of Si and R. And if we take the derivative of this equation, we get the following differential equation that we can solve with the integrating factor. So we get our integrating factor here and multiply both sides of the equation 5 by this, and then we see that the solution n of t is given by the following expression where c is an arbitrary constant. Then we can solve for c by just letting n of 0 be some initial population value, and we get the following value for c. Then we can write the total population at time t as equation 6 here. And to see how the system behaves over time, we take the limit of n as t goes to infinity. Here we see the system is bounded and we can verify its stability at the steady state solutions. We also take into account that the third differential equation, R of t, can be written as n minus s minus I. So we can solve for R of t from the other two equations, which reduces the model to a 2D system. So now we can remove the third equation and study the following two-dimensional system of ODEs. We will perform a phase plane analysis to determine the stability of the possible steady states in the population. So since the two differential equations on the previous slide are nonlinear, we will construct a linearized system where the stability of the steady state solution will be the same for that of the population model. So if we take the partial derivatives of those two equations on the previous slide with respect to each variable, we get the following 4 equations, and then we can write the linear system as the form du dt and dv dt shown here. And for The first phase plane analysis, we're going to use the trivial steady state 0, 0. So this steady state occurs when the birth and death parameter mu is equal to 0. And so plugging that into the system gives the following matrix form for u and v. And we can easily find the eigenvalues of this matrix since it is diagonal. So alpha 1 is 0 and alpha 2 is minus beta. So the first eigenvalue is 0. So that point will be a line of equilibrium. And the second eigenvalue is negative. So this steady state will be stable, but not asymptotically stable. This means that for initial conditions close to this steady state solution, the system will converge. But if we perturb the system too far from that solution, it can diverge from the equilibrium. So next, we're going to also talk about the trivial infection-free steady state. So this considers what happens to the population with 0 individuals with an affinity for punishment. If we let I equal 0 in the first DE, we can solve for S and get the following equilibrium point 1, 0. And as before, we plug this point into the partial derivatives and get the linearized system. We have it again in matrix form, and we can solve for the eigenvalues by using the characteristic equation. We get the first eigenvalue is negative, and that the second eigenvalue is negative as long as lambda is less than n times b plus mu. So if the infection rate is below a particular threshold, no people with a desire to punish will arise out of a population that initially does not contain those individuals. And then next, we'll talk about our numerical simulations.
For our numerical solutions, we used Python, Python SciPy integrate package, and we can see that the one on our left is supposed to be an ideal graph. For our SIR model, we start our recovered people from essentially 0 at time equal to 0. Our aggressive population is few in numbers. It's usually like 2 to 3 people, and we can see that the infected people usually peak over at times equal to around 10-ish, and we can see that it starts to go down. And at the same time, we are seeing that the treated people are increasing rapidly. Meanwhile, we can see the susceptible people are also decreasing with the exponential, exponential decay. On our right, we can see that this is essentially the same case scenario with extreme cases. The infection rate here is rather large, and around time equal to 10, we can see that there's something extreme going on, and that causes the treated people to suddenly reach 0. That has direct result in the susceptible and aggressive people. They both start to peak or over around times after time t equal to 10 years, and we can see that this will not happen in a regular case scenario, but rather an extreme case, which is not likely to happen in real life.
So some additional simulations that we ran were on real populations in society. So we did 2 simulations on DC and St. Louis, and we based our population statistics from stuff that we looked up online. And we based the lambda parameter, how often people get infected, on crime rates. And we based the treatment rate, or the rate that they become non-infected, based on mental health statistics, or how often people seek help for their problems. As you can see here, we don't see the idealized SIR behavior because we have such a larger population with a lower lambda parameter. Finally, we want to talk about some of the limitations and further applications of our project. So one of the big assumptions we made was that the recovered population cannot become susceptible or infected again. Obviously, this is not truly the case in society. So that would be one thing that we would definitely adjust. We also did not add any bias for individuals closer in a population to have a greater desire to punish. We also assume that our parameters are not functions of time, so lambda, beta, and mu do not change over the time in society. And then we also don't account for other variables affecting the stability of society, such as economics, demographics, overall health, climate in society, and infrastructure. Thank you very much for listening to our presentation. We wanted to thank our coach, Anthony Stefan, for encouraging us to compete, the judges at SCUDEM for reviewing our presentation, and Simeode for giving us the opportunity to complete this challenge and present our experiences.